Welcome to The Explainer, where today we're unboxing a fundamental law of physics, Gauss's law. We're going to turn this complex idea into a clear visual story you can actually get your head around.
So let's start with a puzzle. How do you measure something you can't even see, something hidden inside a box that you're not allowed to open? This was a real fundamental mystery for early scientists as they tried to get a handle on the invisible world of electricity.
You see, electric fields are these invisible forces. They're everywhere around electric charges. And trying to calculate their strength and direction at every single point in space, man, that's like trying to map every single raindrop in a storm. It's just impossibly complicated.
So if we can't count every raindrop, what if we just measured how many come through a window frame? That's the big idea, the core concept behind something we call electric flux.
Basically, electric flux is just a way to count the total amount of electric field flowing through some area. Instead of juggling a million different data points, it gives us one single, really useful number that tells us what's going on.
Okay, now here's where it gets really interesting. Get this. If you imagine a sphere around a charge, the total flux, the total number of field lines passing through it, stays exactly the same no matter how big or small you make that sphere. I mean, think about it. As the sphere gets bigger, the field gets weaker, right? But the surface area gets bigger, and those two effects cancel each other out perfectly. The total count is always the same. Wild.
And that one surprising, kind of mind-bending fact, that's the key that unlocks one of the most powerful and, honestly, elegant shortcuts in all of physics.
And here it is. This is Gauss's law. It's a truly revolutionary idea. It says that the total electric field flowing out of any closed surface, our imaginary box, depends only on the total charge you put inside it. Anything happening on the outside, it just doesn't matter for the total count.
This picture illustrates it perfectly. Just look at these four surfaces. The flux through S1, which has a positive charge inside, is positive. Makes sense. For S2, with a negative charge, it's negative. Got it. But look at S3. There's no charge inside, so the flux is zero. And here's the kicker. Check out S4. It's got both charges, so the net charge is zero, and the total flux is also zero, even though it's sitting right in the middle of this really complex electric field. It's all about what's inside the box.
So the crucial point here, the big takeaway, is that for any imaginary closed shape we decide to draw, and physicists call this a Gaussian surface, any charges that are outside that surface don't change the total net flux. Their field lines might go in one side, but they come out the other, so they cancel out. For the final tally, they literally don't matter. Okay, so this law is cool, but it becomes a genuine superpower when we use it on problems with simple shapes, with symmetry. That's where it goes from being a neat idea to a massive, massive shortcut for calculations. So instead of having to wrestle with all this insane calculus, we can just use this simple three-step strategy. First, you identify the symmetry of the charge distribution. Is it a sphere, a line, a flat plane? Second, you choose a Gaussian surface that matches that symmetry. And third, you just apply Gauss's law, and boom, you can solve for the field with some pretty simple algebra. It's all about picking the right tool to make a really hard job incredibly easy. Let's take a long charged wire, for example. We can draw an imaginary cylinder around it. Now, because the electric field points straight out from the wire, the flux going through the flat top and bottom of the cylinder is just zero. Nothing's passing through them. This simplifies the whole calculation so much that we can find the field's strength with just basic algebra. It's such a beautiful and elegant shortcut. Okay, that's the physics. But how does this 19th century law matter today? Well, let's dive into how it's absolutely essential for the technology that's probably in your pocket right now. Remember that little constant in the formula epsilon naught? That's called the permittivity of free space. It's kind of like a baseline for how an electric field moves through a vacuum. But here's the thing. Every material interacts with an electric field differently, and that unique property is called its permittivity. We often talk about this as relative permittivity, or sometimes you'll hear it called the dielectric constant. It just compares a material to a vacuum. And as you can see from this table, the numbers can be way different. Look at tantalum pentoxide. Its value is 26. That means it's really, really good at reducing the electric field inside it. And that's a property that engineers can exploit to design some really powerful electronic components. And this property is the absolute key to a little component you've definitely heard of, A capacitor. You can think of a capacitor as a tiny, tiny battery. But instead of storing energy in chemical reactions, it stores energy directly in an electric field. And what that means is it can charge up and then discharge its energy almost instantly, delivering a huge burst of power exactly when it's needed. And here's the big connection, the reason we're talking about this. The amount of charge a capacitor can hold, we call that its capacitance, depends directly on the permittivity of that insulating material that's sandwiched between its plates. So if you want to build a tiny capacitor that stores a ton of charge, you need to find a material with a really high permittivity. Our entire understanding of how to do this, starting all the way back with Gauss's law, is totally critical for designing all the modern electronics we use every day. So think about it. We started with a simple, almost philosophical question about a locked box, and we ended up with a fundamental law of physics. A law that doesn't just let us peek inside invisible fields, but is also essential for building the high-performance electronics in our pockets. It really makes you wonder, right? What other magic boxes are out there just waiting to be unlocked with the right elegant idea?